This is the 18th video in our series on topology. And before we get started today, I'd like to point out that there was a little bit of an issue with an example in the previous video, video 17. And this example was showing that in a certain function space, there is a set that is closed and bounded but not compact. So here we assumed it was compact, took a finite open cover, and then we had this infinite family of functions gi, and we argued that two of those functions had to be in the same part of the open cover. Well, it turns out that the way that we define those functions gi, well, there was some sort of issue with the domain being from 0 to 1. So in fact, we can't just take any two in one of the sets of the open cover. We take two from the first n plus 1 of those functions in the finite open cover that had n sets. And then that takes care of everything. Okay, so if you watched that video and thought there was an issue, hopefully that clears it up. And if you didn't notice the issue, maybe look back at that video and notice how that needed to be fixed and how that fixes it. Okay, so today we're going to talk about local compactness and one-point compactification of topological spaces. So we'll start with local compactness, which is defined as follows. So X is said to be locally compact at a point X if there's an open set and a compact set, so that X is an element of the open set and that open set is a subset of the compact set. And then we simply say that X as a space is locally compact if it's compact at every point. Okay, so now I want to look through two examples. One example of something that is locally compact and one example of something that's not locally compact. Now let's observe that R with the standard topology is locally compact. And well, why is that? Well, that's because if we take an X in R, then X is an element of, well, a bunch of different open intervals, but we might as well take a simple one like X minus 1 to X plus 1. That's an open set, and that open set is a subset of the closed interval X minus 1 to X plus 1. But of course, the closed interval is compact in R with the standard topology. And now I'd like to also prove that Q is not locally compact. And you might say, well, what topology are we putting on Q? Well, the subspace topology viewing Q as a subspace of R. So now, how are we going to prove that Q is not locally compact? Well, we're going to do it by way of contradiction. So by way of contradiction, suppose that Q is locally compact. And well, if it's locally compact globally, well, that's not a great way to say it, but if it's locally compact everywhere, then it's locally compact at 0. But that means that there exists U inside of Q, which is open, and K, which is inside of Q, which is compact, such that 0 is an element of U, which is contained in K. And then I'm just going to put that all of these are subsets of Q, just to keep in mind that our relative topology or our subspace topology here is happening within the subspace topology on Q. Okay, nice. But now let's notice the following. So that tells us that there exists a V which is open in R with U equals V intersected with Q. That's the definition of the subspace topology on Q. But then by the definition of an open set in the standard topology on R, that means that there exists a number that I'll call delta bigger than 0, such that the interval minus delta to delta is a subset of V. But now, kind of smashing these two previous lines together, observe that means that minus delta to delta intersected with Q is a subset of U. our original open set. Okay, so now what I want to do is take the closure here. And when I say take the closure, I don't mean the closure inside of R, I mean the closure inside of Q. So taking the closure of this left-hand set inside of Q will give us the closed interval minus delta to delta intersected with Q. Now observe that if we were taking the closure within R, we would have just this entire closed interval not intersected with Q because Q is dense in R. But since we're taking the closure within the subspace topology of Q, this is simply what we get. Okay, cool. But then that's going to be a subset of U closure. And again, that's the closure in the subspace topology on Q. But then that's going to be a subset of K closure. But now I want to argue that K closure is K. And why is that? Well, K is compact and K is a subset of Q, but Q is Hausdorff. Now, maybe we didn't directly prove that Q was Hausdorff, but I think you could pretty easily prove that Q is Hausdorff. But let's recall that a compact subset in a Hausdorff space is closed. So that's how we know that the closure of K is equal to K. Now, let's notice this, that we've got this thing right here, which is closed, and then this thing right here, which is compact. Now we're kind of forgetting everything in the middle. So we've got this thing right over here, which is a closed subset of a compact space. But that tells us that our intersection, minus delta to delta intersected with Q, is compact. But now let's show that that is an issue. So we can do that pretty easily. So let's consider the inclusion map. And so I'll call that inclusion map iota, which is the standard name for it. And what it does is it includes Q inside of R. And what I mean by the inclusion map is it takes every point X and sends it to X. But notice that over here the domain is just Q, so it's just putting rational numbers into the set of real numbers. And you can check that every inclusion map of a subspace into the whole space is always continuous. That's pretty easy to check. In fact, that might have been like a homework exercise a long time ago. But then what do we know? We know that the inclusion map applied to this minus delta to delta intersected with Q is compact. And why is that? Well, notice that it's a continuous image of a compact set. But then notice that over here, this is just something inside of Q. So the inclusion map kind of acts like the identity. It's almost the identity. And so that gives us let's see, minus delta to delta intersected with Q. So that thing itself is compact. But now notice that compact implies closed. So what we have here is minus delta to delta intersected with Q is closed in R. And now that was the important thing here is we use this inclusion map to take our compactness in the subspace topology on Q to closedness in the topology on R. But now if a set's closed, then its closure is itself. Well, a lot of things are about to go wrong. First of all, notice that the closure of this inside of R is simply equal to the interval from minus delta to delta, which is not what we started with. But of course, that's a contradiction because we know this thing over here on the right-hand side includes irrational points, but the original thing did not include irrational points. Okay, so again, we got a contradiction here, but that contradicts our original assumption here that Q was locally compact, meaning that it's not locally compact. Okay, so now let's get to this idea of the one-point compactification of a topological space. Okay, here's our big result of the day. So X is locally compact in Hausdorff if and only if there's a compact Hausdorff space Y where X is a subspace of Y and Y only has one extra point from X. In other words, Y minus X is a single point. And moreover, this Y is unique up to homomorphism. And in fact, we'll see that that homomorphism has a nice property. We could put that into the theorem here, but I don't think it's really necessary to write it down. We'll just keep it in mind when we prove the uniqueness. So what's important here is we started with locally compact in Hausdorff, and we are essentially finding some very, very small extension, Y, an extension by a single point that maintains Hausdorffness and then takes away the locally from locally compact and leaves us with just compact. Okay, cool. So we've got an if and only if statement here. We have two things to prove. Well, really three things to prove: forward direction, reverse direction, and then uniqueness. So let's get going with the forward direction. So let's take a point outside of X, and what we'll do is call it infinity. And you'll see that generally this extra point that we tag on to create the compact space, we'll often call this the point at infinity, and we'll just call it infinity. Now you might say, well, how do we know that there is anything outside of X? Well, it could just be some sort of abstracted point that's not inside of X. Okay, cool. And now what we'll do is set Y equal to X union with this point that we're calling the point at infinity. Now what we need to do here is construct a topology on Y so that when we restrict to the subspace topology on X, we have the original topology that we had on X. So let's maybe just note here that we're taking T sub X to be equal to all the open sets on X that are kind of the original open sets on X. Okay, so now let's construct that topology on Y. So I'll call it T sub Y. And what it'll be is it'll be made up of all of the original open sets. So remember we called those T sub X, union with the complement of the compact sets. So this is going to be Y minus K, where K is a subset of X is compact. Okay, cool. And now what we need to do is really show two things here. So the first is that this defines a topology on Y. And then the next thing is that it restricts down to give X the subspace topology, which is the same as the original topology on X. Okay, great. So how do we show that it's a topology on Y? Well, we have a couple of conditions here. First of all, it has to contain the empty set, but notice that the empty set is an element of Tx, which is a subset of Ty. That's because T sub X is a topology from the beginning. And then it also has to contain the entire thing. But let's notice that Y is the same thing as Y minus the empty set. The empty set is compact, kind of trivially, but that means that Y minus the empty set is open because it's the complement of a compact set, but that means that's in T sub Y as well. Okay, so we're good to go there. It contains the empty set and the whole thing. And now it has to be closed under finite intersections, but let's recall that much, much earlier in this sequence of videos, we proved that we could really just show that it's closed under two intersections, and then that inductively shows that it's closed under finitely many intersections. So let's take two open sets, U and V, inside of T sub Y, and let's observe that that's naturally going to split into three cases. And that three cases comes from, well, do both of them come from this T sub X? Or do both of them come from this complement of compact, or does one come from each? And we've got to cover each of those. So let's observe that if U and V come from T sub X, then that means that U intersected with V, is also in T sub x, which is a subset of T sub y. That's because T sub x is a topology, so it's already closed under finite intersections. So that's our first case. Our next case will be U is inside of T sub x, and then V equals y minus k, where k is compact. But now let's look at this. Let's look at U intersected with V in this case. But now using the shape of V, we know that this is U intersected with y minus k. But now I'm going to make a quick change here. Since U is in T sub x, U is a subset of x. But if U is a subset of x, I can just go ahead and take this y right here and replace it with x. Because, well, all the parts in y that are not in x get wiped out by the intersection with an obvious subset of x. Okay, so now we've got U, which is open in x, and then we've got x minus k. Observe that k is compact in x, but compact implies closed because we're in a Hausdorff space. So that means x minus k is open because k is closed. So here we've got the intersection of open with open, meaning that this is in fact open. And not only that, but it's inside of T sub x. It's a subset of x. Okay, good. So anyway, we got it working for this second case as well. So now let's say that we have U equals y minus k1 and V equals y minus k2. And notice that that implies that U intersected with V is going to be equal to y minus k1 union k2. Just the way that complements and intersections and unions work with each other. But now again, we can argue that that is also open, and that's because k1 and k2 are compact, meaning they're closed because they're compact subsets of a Hausdorff space. We just used that. But then the union of two closed sets is still closed. So k1 union k2 is also closed, but now we're taking the complement of a closed set, which is an open set. So that means that this is inside of T sub y. Well, I guess all we really needed was k1 and k2 to be compact, because then it would be of this form right here. Okay, great. So now we've got that this is closed under finite intersections. Now we need to look at arbitrary unions. Now we'll show that an arbitrary union of open sets in Ty is also in Ty. And so we're going to take two families of open sets, one that are of this T sub x variety and one that are of this y minus k variety. So let's call those U sub I, which are in T sub x, as I runs through an entire indexing set I. And then our next variety will be maybe V sub j, which is y minus k sub j, as j runs through some sort of indexing set capital J. And now let's look at the union over all I in I of U sub I, and let's set that equal to U. But observe that that's already in T sub x, because we know T sub x itself is closed under arbitrary unions, given the fact that it is a topology. And now let's look at V, which is equal to the union over all j in J of V sub j. But now let's observe that that's going to turn into y minus the intersection over all j in J of k sub j. But then you can prove, and I think maybe we proved this in the past, that if you take an arbitrary intersection of compact sets, you still get a compact set. So that means that this arbitrary intersection is compact, which means y minus that compact set is open in the sense of this part of T sub y already. So this is in T sub y. Okay, now we just have to see what happens when we take the union of something from T sub x and something from this other bit right here. And observe that we only need to look at one from each. And that's because we can just take any larger collection that includes both types and first maybe do this procedure on them to break them down into open sets that are either in T sub x or in the other type, and we'll be good to go there. So anyway, in like a bit of a conclusion or a summary, we only have to take one open set like this and one open set like this to take the maybe different type of union condition. Okay, so anyway, let's take U inside of T sub x, and we'll take V equal to Y minus K. And now let's look at U unioned with V. But observe that that's going to be U unioned with Y minus K. Now, but notice just by doing basic set operations, this is equal to Y minus, let's see, it's going to be K minus U. Okay, great. But then it's pretty easy, and I guess I'll leave it as a homework exercise to show that K minus U is compact given the things that we're starting with, and thus Y minus K minus U is open in this sense right here. Okay, so there we have it. Our T sub y satisfies the axioms for this to be a topology. And so that does define a topology on Y. Now, the next thing to prove, which I'll leave as a bit of a homework exercise, is to show that if you view X as a subspace of T sub y and give it the subspace topology, that is equivalent to taking the topology T sub X on X from the very beginning. And that way we can really view this Y as a direct extension of X that maybe also not only extends the set, but extends the topological structure. Okay, good. So now that sets up our topology on Y, and now we have to prove that Y is compact and Hausdorff to finish this direction. All right, so now we'll prove that Y is compact. So let's start with an open cover of Y. We'll call that U. And now let's note the following, and that is if we take all open sets of the form T sub X, so in other words, original open sets from X, this does not cover Y. And well, I think that's pretty clear. Notice that none of the sets in this T sub X contain our point at infinity. That's because infinity is not inside of X. So if none of them contain that point, they cannot cover Y. But well, what does that mean? So that means there exists a compact set K inside of X such that Y minus K is an element of our U. Because if this were not the case, then all of the open sets inside of our open cover would have come from T sub X, but we just proved that it would be impossible for them to cover Y. So it has to have one of these other flavors of open sets. Okay, so now what we want to do is form another set that I'll call U naught or U zero, and that's going to be everything of the form U intersected with X as long as U is inside of our big script U and U is not equal to Y minus K. Okay, so something like that. So notice that this is an open cover of, how do we know it's an open cover of K? Let's notice that by the rules of the construction here, the only thing that it's really allowed to miss is the complement of K in X. And that's because U is not Y minus K, and then we're doing this U intersected with X. So again, the only thing that this is allowed to miss, if you will, is the complement of K in X. But that means it's an open cover of K. But notice that K is compact, so that means there is a finite subcover. So let's take that finite subcover and call it U1 to UN. K is a subset of U1 intersected with X, union U2 intersected with X, union all the way up UN intersected with X. Okay, cool. Now I guess over there I was a little bit not careful. The finite subcover is not U1 to UN. Those U's were from the original open cover, but the finite subcover is actually this form of this intersection. But as we'll see, there's really no issue with that because we're about to take y and write it as k union the complement of k. But now we can observe that that's equal to u1 union all the way up to un union y minus k, kind of by an obvious construction. But notice that u1 up to un came from our original open cover, but then just adding one more of them keeps a finite number of sets, so we've done it. We started with an open cover of y and we formed a finite subcover, but that's exactly what we need for y to be compact. Now let's prove that y is Hausdorff. All right, now we'll prove that y is Hausdorff. So let's take x and y, little x and little y and y, with little x not equal to little y. And now let's, quickly notice that there's a very simple case of this. And that is if x and y are both inside of x, we are done. And well, why are we done? Well, that's because x is Hausdorff. So that means we can find two open sets inside of x where x is in one of them, little y is in the other one, and they do not intersect. But open sets in x are open in y by the way that we constructed y, so we're okay there. So now we might as well take one of these to be the extra point. Notice we can't take both of them to be the extra point because then they would be equal. So let's maybe set y equal to this point at infinity. And then after that, we want to find a point, a set u, which is open in x, and a set k, which is compact in x, where we have little x is an element of u, which is a subset of k. So that's using the local compactness of x. So let's notice that since all of this is happening inside of x, we have infinity is not inside of k. But that implies that infinity is inside of y minus k. Oh, but now we're essentially done because we've got u intersected with y minus k is empty. And well, that's because u is a subset of k. So if u is a subset of k, when we intersect it with the complement of k, we necessarily get the empty set. And well, let's step back and see what we've done. We took 2 points that were not equal in y. We argued that one of them had to be this point at infinity. And then we found 2 open neighborhoods, one of them containing x, one of them containing infinity, that were disjoint. But that's exactly the definition of Hausdorff. Okay, so that finishes this forward direction. Now let's prove the reverse direction. All right, so now let's get to it. So for the reverse direction, we start with all of this stuff over here and we prove that x is locally compact in Hausdorff. But let's notice that y being Hausdorff immediately implies that x is Hausdorff. So I'll let you all check that, but anytime you've got a topological space that's Hausdorff, something with the subspace topology of that topological space is also kind of immediately Hausdorff. So we're okay there. Now let's set y minus x equal to the point at infinity again. I guess we could give this a different name, but let's call it infinity just as we did before. And we know that's a single point because that's in our assumption for this direction of the proof. And now let's prove that we in fact have a locally compact space here. And what I mean when we have one, I mean x itself must be locally compact. Okay, so let's suppose that x is inside of x. And what we'll do is find open sets u and v, which are open in y, such that x is an element of u, infinity is an element of v, and then u intersected with v is the empty set. Okay, great. But now what I want to do is set K equal to the complement of V. But now let's notice that that is definitely closed inside of Y because it's the complement of an open set in Y. But now Y is compact, so any closed set of a compact space is compact. So that means K itself is compact. Okay, great. But then, since infinity is an element of K, that tells us that infinity is an element of V. That tells us that infinity is not an element of K, meaning that K is a subset of X, because the only thing that differs between X and Y is infinity. So if K is a subset of Y, but it doesn't contain infinity, then it must in fact be a subset of X. But then let's also observe that putting these two things together, U intersected with V is empty, and then K is the complement of V, tells us that we have X inside of U, which is a subset of K. But taking a step back, that's exactly what we wanted to have here. We took a point X, we found an open set and a compact set, both subsets of X. And the original point was an element of the open set, which was a subset of the compact set. But that's exactly what we need for X to be locally compact. All right, so now we're done with the if and only if statement. Now we need to prove the uniqueness condition. All right, so for uniqueness, let's suppose that we potentially don't have uniqueness and show that these spaces have to be homeomorphic, and that will prove uniqueness up to homeomorphism. So let's set Y equal to X union infinity 1 and Y2 equal to X union infinity 2. And let's suppose those satisfy this condition. And by this condition, I mean all of this stuff in here in the theorem. And now I want to define a function. And my function will go from y1 to y2. And I want to say that f of x is equal to x for all x inside of x. So in other words, it simply fixes the points from x. Now we could write that as f restricted to x gives us the identity function on x if we wanted to be fancy about it. And then I guess you could probably guess that we'll have f of infinity 1 equals infinity 2. I think that's a pretty clear way to define this function. And now what we need to do is show that this function is a homeomorphism, which means we need it to be open and we need its inverse to be open. I guess it's pretty clearly bijective already, so those are really the only things that we need to prove. So let's go ahead and show that it is continuous, and then it'll be very, very similar to show that the inverse function is continuous, so I'll leave that for you. So let's suppose that V is a subset of Y2 and it's an open set. Now, I'd like to observe that that's going to pretty naturally break into two cases. So the first case is that V is itself just a subset of X. So in other words, infinity 2 is not an element of V. But in this case, it's pretty straightforward. Notice that the inverse image of V is simply equal to V. And that's because F restricts to the identity function. But this original V was open in X, but then this V started out as being open, so of course the identity function is not going to make it not open. Okay, so now let's look at the other case. And the other case is that V is not a subset of X, but that can only be satisfied if infinity 2 is inside of V. But now let's look at this. Let's look at K, which is equal to Y sub 2 minus V. But now this thing is closed, and not only is it closed, but it's a closed subset of X. But now K is the complement of an open set, which means it's closed. And not only is it closed, but it's a closed subset of X. Okay, good. But now let's look at the pre-image of V. And let's observe that the pre-image of V now, using this rule right here, is simply y sub 1 minus the pre-image of K. But now since K is inside of X, f acts as the identity function. So this is simply y1 minus K. But again, K was closed, which means its complement is open. So let's see, regardless of how you slice it, if you start with an open set and find its pre-image, it is still open, meaning that we have a continuous function. And like I said, essentially the same argument shows that the inverse function is also continuous, meaning we have a homeomorphism. All right, so now let's see what we can do with this theorem. All right, so here's a classic example. The one-point compactification of Rn is Sn. So what do I mean by Sn? I mean the n-dimensional sphere. So that naturally lives in Rn plus 1. In fact, we could say that Sn is equal to x1 up to xn plus 1 inside of Rn plus 1, such that x1 squared added all the way up to xn plus 1 squared is equal to 1. That's like the unit n plus 1 square. So as a concrete example, let's look at the circle and the line. So here we've got S1 and here we have R. So what I mean by S1 is the one-point compactification of the line is there's an obvious homeomorphism from S1 to the one-point compactification of the line. So that means we need to construct a homeomorphism from S1 to R union infinity, where R union infinity has that topology that was defined in that previous theorem. So by that, I mean a basis for open sets over here is built from sets of the form intervals A and B, where A and B are R, or complements of simple compact sets. So a complement of a basic compact set would look like minus infinity to A, and then union B to infinity, but we need to throw in the point at infinity there. So I'll say union that point at infinity. Okay, so open sets like this form a basis for that topology on that one-point compactification of the line, and this basis creates the same sort of topology that we had in that theorem. So now we need to figure out how our function takes a point from S1, the circle, and maps it into and onto this one-point compactification of the line. So the general geometric way to think about this is to put a circle on top of a line and send the north pole to the point at infinity. And then we'll sort out how to do all of the other points using the following trick. So let's say we've got an arbitrary point x here that's on the circle, and what we want to do is find the line between the north pole and x. And observe that that line between the north pole and x will intersect the real line down here at exactly 1 point. And we'll call that 1 point f of x. Okay, cool. So that is how we define our function. And now we can kind of graphically, if you will, check that this is in fact continuous by looking at pre-images of, well, we don't even have to look at an arbitrary open set in R union infinity. We just have to look at an open set from the basis. So let's notice if we had an open set like this in the real line, its pre-image, well, it's pretty obviously of this form right here. It's this arc on the circle. And then if we instead had an open set that looked like this, so perhaps it went out in both directions like this, and then also included infinity, then what would we have? We would have something like this that goes through the North Pole. So just kind of graphically, we see the pre-images of two types of open sets that we have here are in fact open sets in the circle. So we have a continuous function here. Now it's not so far from this point to prove that we have a bicontinuous function. That is, the inverse function is also continuous, but I'll leave that for you to check. Okay, so that should give us some sort of idea for why this one-point compactification of the real line is homeomorphic to the circle. Now, if you don't like this graphical interpretation and you'd rather have some sort of formula, let's look at that. All right, so if you'd rather have a formula, here's how you can get at that. So let's say our circle is simply all the points in R2 where x squared plus y squared equals 1. And let's do the same kind of thing, except instead of putting the circle on top of the line, let's cut the circle with the line. So just to be clear here, this is the y-axis and there's the origin. So we're going to do the same kind of thing where we took a line between this point right here, which is the North Pole, in the case that we have these coordinates 0, 1, and then through an arbitrary point on the circle. Now that arbitrary point is going to take the form x comma y because we're embedding all of this in the real plane. And now we'd like to assign that to something down here, which we'll call f of x, y. And the way we'll do that is to find the explicit equation of this line, which isn't so bad. Notice the explicit equation of this line using point slope form is going to be equal to y minus 1 over x times t plus 1, where t is our variable there. So that's the equation of that line. And so notice that this intersection point right here is simply a 0 of this function. So in other words, it's going to be when y minus 1 over x times t equals minus 1. But we can pretty quickly solve for t here and see that that's going to be x over 1 minus y. So that's the value right here. So that means that f of x comma y here, being this intersection point, is simply x over 1 minus y. So that means, well, we have our function. So we can define f from S1 into R union, the point at infinity, piecewise as follows. So f of x comma y will equal to, let's see, x over 1 minus y if y is not equal to 1. Notice that y is equal to 1 only a single place in the circle up here. So that's going to define where the function sends every point along this circle except for the North Pole. And it's going to send the North Pole, which is the place where y equals 1, to our point at infinity. And now I'd like to note that behind all of this, we have a restriction on x and y. And that restriction is that x squared plus y squared must always be equal to 1 because we're on the circle in the first place. Okay, so now we've got this formula. Maybe you could, if you wanted to, prove that this defines a homeomorphism, where the topology we take on S1 is the subspace topology, where S1 is a subspace of the plane. Okay, so now I'm going to leave you with some exercises. All right, so here are two exercises. The first is to mimic the last example to construct a function from S2 to the one-point compactification of R2, or generally Sn to the one-point compactification of Rn. And let's maybe go ahead and try to find a formula in each case. And here's a little picture of what's going on here. We've got this sphere laying inside of a plane. And you can think about taking out the North Pole and then taking an arbitrary point x, y, z on the sphere. And then notice that that's going to intersect our plane at exactly one place, f, x, y, z. And you'll have to find what that is. That'll define where you can send everything except for the North Pole. And then I think, as you could guess, the North Pole will be sent to this point at infinity. Okay, so next up, let's show that the one-point compactification of the natural numbers is homeomorphic to the set containing 0 unioned with reciprocal of all natural numbers. And that's a good place to stop.